In this video, we're going to spend a little bit more time drawing Lewis structures and learning some exceptions to the rules. And we'll also learn about VSEPR theory, which is something we're going to be using quite a bit in determining molecule shape. So with the octet rule, recall that electrons need to be arranged so that their valence shells are filled. But there are some times when the octet rule won't work because of where certain elements are found on the periodic table. So we'll go over some of those exceptions right now. So here are some extra octet rules. So hydrogen is stable with only 2 electrons. We talked about that already because hydrogen is in period 1. It can only have a maximum of 2 electrons in the first valence shell. But then atoms like beryllium, boron, and aluminum, they can never have enough electrons to complete their octet because they have less than 4 electrons in their valence. So they're known as electron deficient atoms. Then atoms in period 3 and higher can actually share up to 12 electrons. So they have what is called an expanded octet. So first of all, we have compounds with incomplete octets. So these compounds will be stable with incomplete octets because they are electron deficient. So we look at boron trifluoride. We have boron having 3 electrons and each fluorine has 7. So we have 3 plus 3 times 7. So that's going to be 24 electrons to distribute. So you might think, well, boron could have enough, but if we draw this, so B and then each of the F's, so we have our 3 bonding pairs around. So now boron's done. It can't get another one. It doesn't have any more electrons to share. So that means that fluorine gets the rest. So we had 6, so we have to put the remaining 18 somewhere. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So this is how you would draw BF3. BeCl2. So we have beryllium, and then we have 2 chlorines. So we'll draw our initial bit here, but first we need to figure out how many electrons we have to share around. So first we have to find out how many electrons we have to share around. So beryllium has 2 electrons and chlorine has 7 each. So there's 14, 15, 16. So a total of 16 electrons. So we've drawn our bonding pairs. And so that's only 4 for beryllium. But now we have 12 more, so we're just going to put them all around chlorine. So that's the 12 more. So now we have satisfied chlorine's octet, but we can't satisfy beryllium's. So that would be examples of molecules that would have incomplete octets. So expanded octets, so atoms in group 3 or higher can have expanded octets. So an example that we'll use is sulfur hexafluoride. So sulfur has 6, and then fluorine each has 7. So that gives us 48 electrons to distribute. So we have sulfur, and then we're going to draw 6 fluorines around. 1, 2, 3, 4, 5, 6. So the first thing is we'll put our bonding pairs around like so. So that's 2, 4, 6, 8, 10, 12. So we still have 36 to distribute. (13, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. So that's how you would draw sulfur hexafluoride. As you can see, sulfur now has 12 electrons in its octet, which is more than most are allowed, but because it's in period 3, it has expanded octets. So resonance structures. So when molecules contain multiple bonds, like double, triple bonds, along with their single bonds, there's multiple possible Lewis structures, because you could have the double bonds in any of those positions. So those different arrangements are called resonance structures. And the number of resonance structures is equal to the number of positions the multiple bond could occupy. So for instance here, this is the carbonate ion. The double bond could be here, or it could be here, or it could be here. So you can see that there's 3 possible resonance structures. So the double bond could be in any of those positions. However, resonance structures are special. The double bond doesn't rotate like we are imagining. They're actually hybrids. So they don't alternate between the different options. Instead, they become a blend of the options. So all of the bonds will be the same length and strength, instead of having a double bond in one position and the 2 single bonds for carbonate as we just looked at. So they'll actually have a bond length and strength in between the single and the multiple bond. So we'll look at an example of that in a little bit. But this is kind of like chemists will use the MULE analogy to help explain this. It's explained a little bit more in depth in our cognitive textbook if you would like to read the analogy. So basically it's like a mule. So as you know, or maybe you don't know, a mule is a cross between a horse and a donkey. It's a brand new animal. It doesn't flip from being a horse and a donkey, it's a mule. That's the way you could explain a resonance structure. It doesn't flip between the double and single bonds or triple and single bonds. It is a blend between that. So there are ways that we'll show that notation, and we'll actually look at an example to see the difference between bond length and strength in our next bit of our video. So our first example is ozone. So ozone is O3, and it's a resonance structure. It can alternate between the double bond being here or here, or here or here. So its bond length is actually 127 picometers, and it's a blend between the oxygen single bond, which would be 148, and the double bond, which would be 121. So the whole thing, their bond lengths are actually not 121 and 148. Instead, their bond lengths are 127. And this is one way of demonstrating the resonance, that it's an intermediate between a single and a double bond. When we study organic chemistry, you'll learn a lot more about benzene. Benzene is this interesting molecule here. Its chemical formula is C6H6. So it's a ring structure, a hydrocarbon ring that's 6 carbons around, so it's a hexagonal molecule. And every other bond is a double bond. So it looks like that. So one way chemists sometimes represent hydrocarbons that are in cyclic form is just by drawing the shape. So if you just drew in a hexagon, you would know that it was a cyclic hydrocarbon with 6 carbons in it, and it can alternate with double bonds on every other one. So it could be this, or it could be this. But rather than drawing this, chemists draw this to show that there's resonance, that those double bonds could alternate. So it's a hydrocarbon ring with alternating single and double bonds. So this would be the correct form for drawing the resonance structure for benzene. So we'll talk now about VSEPR and how we can use that to figure out the shapes of molecules. So VSEPR is the valence shell electron repair repulsion theory. So basically, electron pairs repel each other. So because those electron pairs repel each other, it forces molecules into particular shapes. So we use VSEPR theory to predict the 3D shapes of molecules. And in order to do that, we only look at the valence shell electrons of the atoms, just like for everything else. So we're going to practice with VSEPR. So there are 3 steps for predicting the shape of a molecule. The first thing is to draw. So draw the Lewis structure for the molecule. And then you're going to count. So you're going to count the total number of bond pairs, so the number of bonds surrounding your central atom. And then you're also going to count the lone pairs of electrons. So those are called sometimes electron domains around the central atom. So once you've done that, you can then use that information to determine the shape of the molecule. You can also build the molecule and then look at the shape when you find the result. But this is how you could determine the shape before even building the molecule. So if there are two electron domains, those molecules will be linear. So their bond angle will be 180 degrees because those electron pairs will have repelled each other as far apart as they can be. So then that would be 180 degrees between each of the bonding pairs. So it's a linear molecule. Two examples of linear molecules would be carbon dioxide, this one right here, and this is ethine. You'll learn about that in organic chemistry. So again, two electron domains, so it's a linear molecule. If a molecule has three electron domains, there will be two options for shape. So one, it could be trigonal planar, or if it has a lone pair of electrons as one of the electron domains, it'll have a V shape or bent shape. So two examples would be BH3, so it has a trigonal planar, and then CO3, so the carbonate ion, would have trigonal planar. For these ones, their bond angle will be 120 degrees. So again, they'll have separated. So the way you can figure out bond angle for the most part is how many electron domains, divide that by 360. So for linear, it was 180 degrees. For trigonal planar, it's 120. So for 4 electron domains, these molecules will have a tetrahedral, a trigonal pyramidal, or a bent shape, depending on lone pairs of electrons. So the first example is methane. So it has carbon with 4 hydrogen atoms attached. So you'll see these funny little things. So the first few molecules we've been looking at have been like 2D shapes, so they've been planar. These ones now are not planar, they have a 3D shape. So to draw and show electron pairs going into and out of the page, this is showing that this hydrogen is going like into the page, and this one is coming out. So it actually has a 3D tetrahedral shape. This one, so that's methane, and its bond angles are 109.5 degrees. Trigonal pyramidals, so an example would be ammonia. So it looks more like a pyramid. It doesn't have a bonding pair up here. It's a lone pair of electrons. So it looks like a little pyramid or tripod almost standing on the page. So one part will be going into the page, this one's coming out, and that one's just flat on the page. So their bond angles are 107.8 degrees. And then a bent shape or a V shape, an example of that would be water. So there's now 2 lone pairs of electrons, and then the two bonding pairs. So that's why we draw water as a bent shape, because of these 2 lone pairs of electrons repelling the bonding pairs. So this is going to be 104.5 degrees in the bond angle. So this table kind of assists in figuring out the shape of your molecule. You might find it helpful. So these are all examples of some of the ones that you'll need to know. So linear, trigonal planar, tetrahedral, all the ones that we talked about. And it talks about how many bond pairs or lone pairs you have, so the total pairs, and then the shape, and then some examples. So this table might be useful for you to explore a little bit more. So now we've been asked to use Lewis structures and the VSEPR theory to predict the geometry of the NH3 molecule. So if you remember, nitrogen has 5 electrons, and then hydrogen each has 3 to share. So that's equal to 8. So we'll draw our nitrogen and our 3 hydrogens like so. We'll put a bonding pair between each one. That's 2, 4, 6. We still have 2 more electrons to distribute, so we'll put the lone pair up there. So then we can see that there are 3 bonding pairs and 1 lone pair of electrons. And if we go back to our table, or from what we learned, that's a total of 4. So our shape is trigonal pyramidal. And then actually we should be drawing, so 1 will be coming into the page and 1 will be going out of the page, and then 1 flat. So that would be how you would draw it. So it's trigonal pyramidal. So the next one, we're talking about carbon tetrafluoride. So carbon has 4, and then we have 4 fluorines, which are each 7, so 28. So that's equal to 32. So we'll put our carbon in the center, our 4 fluorines with their bonding electrons. So they're bonding pairs, so that satisfied chlorine, but that's only 8, so we need to distribute the remainders. So 6 more on each one. So again, if we looked back at the chart, or from our remembering, when you have 4 bonding pairs and no lone pairs of electrons, you have a tetrahedral shape. So again, we would need to draw 1 coming into the page and 1 going out of the page, like so. So it would be demonstrating that it's tetrahedral. So if you were to draw it, it would be more like, and this one would be coming out and that one would be going back there. So tetrahedral.